Okay, in this video, we're actually going to be talking about a third type of asymptote line, and it's called an oblique or a slant asymptote. And if you remember correctly, your rule was for a horizontal asymptote, when the top degree was bigger than the bottom degree, there was no horizontal. Well, in that case, that's where these oblique asymptotes or slant asymptotes come into play. So here's going to be your rule. When the degree of P of x is exactly one more than the degree of the bottom, which we called Q of x, the graph will have a slant or an oblique asymptote. And the way I like to remember this, I'll explain in just a second. It says the equation of the oblique asymptote is y equals mx plus b is the quotient of P of x over Q of x, ignoring the remainder. So the way I like to do this is, well, think about this. If the degree of the top is bigger than the bottom, think about back when you did fractions, what we called improper fractions. When I had an improper fraction, how did I change it to a mixed number? I divided the top by the bottom. 3 went into 5 one time with 2 left over. That's exactly what we're going to be doing here. When your degree on top is bigger than the degree on the bottom, we're going to use long or synthetic division to divide P of x by Q of x. This is how we find this equation. We're going to write the equation of the oblique asymptote using the quotient, ignoring the remainder. And when we get later on in our other courses, we'll explain a little bit why we can just do this, why we can ignore the remainder. So let's try this. Find the equation of the oblique asymptote or the slanted asymptote. So you have x squared minus x minus 14. Notice the degree of the top is 2, degree of the bottom is 1. So that's, since it's one more, we're going to have this oblique asymptote. We're going to use synthetic division, divide it out. I have a 1, a negative 1, and a negative 14. Bring it down, multiply, gives you negative 5, multiply, gives you 20, 6 is your remainder. So this is equal to x minus 5 plus 6 over x plus 4. So your oblique asymptote is simply this part. Y equals x minus 5 is going to be the asymptote line that this follows. The next one, you have, let's rewrite this, synthetic division, divide it out. The degree of the top is 2, bottom is 1, so it's improper. So you have 3, negative 7, and 0. Bring it down, multiply, add them together, multiply, add them together. So this turns into 3x plus 2. This was your remainder, so plus 6 over x minus 3. So your oblique asymptote is y equals 3x plus 2. And it's as simple as that. Okay, number 3. Now here's the problem. We cannot use our shortcut for synthetic division because it's going to mess up if we are dividing by, because when you're dividing by the negative 2/3, which the shortcut would give you, it's going to mess with your factors. So therefore, we're going to have to use long division here. So we're dividing by 3x plus 2. We have 6x squared plus 4x minus 11. 3x into 6x squared gives you 2x. Distribute it, be 6x squared plus 4x. Subtract it. Cancels. This gives you 0x, bring down negative 11. 3x, we go into 0x plus 0 times. That would give you 0x plus 0. Subtract that, and that gives you negative 11 as a remainder. So that'd be minus 11 over 3x plus 2. Therefore, your oblique asymptote would just be this part, y equals 2x. Number 4. Degree on the top is exactly 1 higher, so we do have to use long division here as well. So we're dividing by x squared plus 2x minus 3 into x to the third plus 3x squared plus 0x plus 0. X squared goes into x to the third x times. Distribute that out. That'd be x to the third plus 2x squared minus 3x. Let's subtract that. That cancels. 3 minus 2 gives you 1x squared. 0 minus negative 3 gives you a positive 3x. Break down the 0. X squared into x squared goes one time. Distribute that out, gives you x squared plus 2x minus 3. When you subtract that, cancels, 3x minus 2x gives you 1x, 0 minus negative 3 gives you plus 3. So that gives you plus x plus 3 over x squared plus 2x minus 3. So that's what you get when you divide. However, just for the oblique asymptote, we're only worried about the quotient. So y equals x plus 1. Okay, starting with number 5, it says graph each function and identify its key characteristics. Let's start out with our domain restrictions. The bottom cannot be 0, so here x is not equal to 0. And again, the next question is that going to be a whole or is that going to be a vertical asymptote? Since plain x is not a factor of the top, because when you factor the top, you have an x plus 3 and an x minus 3, that's difference of squares, which factors into conjugates. Since single x is not a factor of the top, then that's going to be a vertical asymptote located at x equals 0. You have no holes. Now, horizontal asymptotes, let's look at it. Go back to here. Anytime the degree on top is greater than the degree on the bottom, you have no horizontal asymptotes. You're going to have an oblique asymptote here, or a slant asymptote. Now here, we don't have to use synthetic or long division. We can actually just split this. And we can say f of x is equal to, we can do x squared over x plus or minus 9 over x. And we can just use our basic rules of exponents here. X squared over x, that's going to be x minus 9 over x. Now here's how you have to look at these, because we haven't been exposed to one of these yet. This would be the remainder term, because you are dividing by x, so therefore that minus 9 over x is going to be the remainder term. This is going to be your oblique asymptote. So we have a slant asymptote at y equals x. So let's go ahead and plot our vertical asymptote and our slant asymptote on our graph. So there are your two asymptote lines. Now let's find our x-intercepts and y-intercepts. To find an x-intercept, we plug in 0 for y, which means, again, the top has to be equal to 0. The only way that this whole function can equal 0 is if the top is equal to 0. So therefore, you have x plus 3 times x minus 3 equals 0. So that's going to be an x-intercept at positive 3 and an x-intercept at negative 3. So you can write that as you have x-intercepts at positive and negative 3, 0. Your y-intercept, we're going to have to set 0 equal to x, which is a problem because if you set x equal to 0, then that means the bottom would equal 0. X cannot be 0, and you can see you had that vertical asymptote there, so there are going to be no y-intercepts. So now you can graph it from here because we know that our graph is going to follow this vertical asymptote, and we also know that our graph is going to follow this oblique asymptote. So it's going to follow here, and then it's going to keep going, and it's going to follow here. So your graph is going to look something like this. The range, notice there's no breaks in the graph. There's going to be no y values not covered. So therefore, your range will be all values from negative to positive infinity, or you can just put all real numbers. Number 2. The degree on the top is bigger than the degree on the bottom, but let's go ahead and take care of all of our domain first. There's only one restriction. X cannot be negative 1. Let's find out if you have a whole or a vertical asymptote at that negative 1 by factoring the top. The top, again, is going to be our slip and slide method. So that's going to be x squared minus 3x minus 40. Two sets of parentheses, x and x. That's going to be a negative 8 and a positive 5. You divide by the 2 that you slipped. And that's going to factor the top into x minus 4 times 2x plus 5. The bottom is x plus 1. Since it is not a factor of the top and bottom, there will be no holes. But you will have a vertical asymptote at that x equals negative 1. Let's go ahead and now find, since the degree of the top is greater than the degree of the bottom, let's go ahead and find our slant asymptote. Again, the method for finding the slant asymptote is, since this is an improper fraction, we're going to divide it. We can use synthetic division here, so we're dividing by x plus 1. We have 2, negative 3, and negative 20. Bring down the 2 and multiply. Combine those, negative 5, multiply. and you get negative 15 remainder. So therefore, this function is also equal to 2x minus 5, and the remainder will be minus a 15 over x plus 1. That's the divided version. So therefore, this part is going to be your slant asymptote. So you have a slant asymptote of y equals 2x minus 5. So let's go ahead and graph those. And a reminder, we can graph this in slope-intercept form. Slope's 2, y-intercept's negative 5. So 1, 2, 3, 4, 5. Change colors here. So you have negative 5, rise 2, run 1, rise 2, run 1. Continue doing that. That's going to be your slant asymptote. So again, let's graph those. So there's your two asymptote lines. Let's go ahead and find the x and y intercept. To find an x-intercept, you set y equal to 0. And again, the only way that a fraction can equal 0 is if the top is 0. So therefore, you get an x-intercept of 4 and negative 5 halves. So let's do our x-intercepts are at 4, 0 and negative 5 halves 0. And we can go ahead and plot those 2 points. So 4, 0, 1, 2, 3, 4 zeros right here. And negative 5 halves 0, that's negative 1, 2 and a half. 0 is located right here. We will have a y-intercept this time, we should. To find a y-intercept, let's plug in 0 for x. So this would probably be our best place to plug in 0 for x, because this goes away, this goes away, this goes away, and leaves you with negative 20 over 1. So 0, negative 20 is going to be your y-intercept. So that's going to cross way down here. So what we're going to have is we're going to have our function following this direction and getting closer and closer to our vertical asymptote, and then it's kind of following up through here, getting closer and closer to our slant asymptote. And then the exact same thing happens on the other side. As we get close here, we're going to follow here, and as we come down, we're going to follow our slant. So our function will look something like that, to where our slant here we're getting closer to on this side, and our slant up here we're getting closer to on this side. Our range, notice there is all values, so negative and positive infinity. Horizontal asymptotes, we had none, because you're not going to have a slant and a horizontal asymptote. You're going to have one or the other, but not both. Number 7, we're going to have to use, let's see, well, first off, let's do our domain. X cannot equal 1/2. Set the bottom equal to 0. So again, what happens at that 1/2 is going to be either a vertical asymptote or a hole. Let's factor the top using slip and slide to C. So we'll come down here to do it. That'll be x squared plus 11x minus 60. Two sets of parentheses will be an x and an x, a positive 15 and a negative 4. Divide by the 6 that you moved. These will not divide, but they will both have to be reduced. That'll be x plus 5 halves and x minus 2/3, which will turn into 5. Let's see, bring the tops back up, 2x plus 5 and a 3x minus 2. And the bottom is still, again, 2x minus 1. So there's your factored form. So since that 2x minus 1 on bottom is not a factor of top and bottom, that's going to be a vertical asymptote. So at x equals 1/2, you have a vertical asymptote. You have no holes. So now let's talk about our horizontal asymptotes or slant asymptotes. And again, the way you can find that is by looking at degree. Since the degree of the top is greater than the degree of the bottom, then we have a slant asymptote. So we'll have no horizontal. To find our slant asymptote, we are going to, again, use long division. 2x minus 1 divided into 6x squared plus 11x minus 10. 2x into 6x squared goes 3x. Distribute it. That'd be 6x squared minus 3x. Subtract the 2. Cancels. 11 minus negative 3 is 14x. Bring down negative 10. 2x into 14x goes 7 times. 7 times 2x is 14x minus 7. When you subtract that, 14x's cancels. Negative 10 plus 7 gives you negative 3. So there's your remainder. Minus 3 over 2x minus 1. So therefore, your slant asymptote is going to be located at y equals 3x plus 7. And that's the only thing we'll need that for. So let's go ahead and graph our vertical asymptote and our slant asymptote. Okay, now let's find our x-intercept and our y-intercept. Again, to find an x-intercept, set y equal to 0. Solve. The only way that that can be true is if the top is equal to 0. So you have 2x plus 5 or 3x minus 2 have to equal 0. So that's going to be a negative 5 halves or a positive 2/3 will be your two x-intercepts. So negative 5 halves, 0, and 2/3, 0. Let's go ahead and plot those points. 2/3, 0 will be about right in here, nearly right on your vertical asymptote. Then negative 5 halves will be negative 2.5, 0, which is nearly on the slanted asymptote. Now let's find the y-intercept. Find the y-intercept, let's plug in 0 for all the x's. And again, the easy way is just plug it in right here. You're left with negative 10 over negative 1, which would be a 10. So 0, 10 is going to be your y-intercept. And that's going to be located somewhere up in here. So it's not, you're not going to see it on your graph. Just to give this more of a look, let's plug in a couple more points just to see what we get to better shape our graph here. So here I plugged in just a few values. 1 got 7, plugged in negative 1, got 5, plugged in negative 2, got 1.6, and I plotted those points. And just a reminder, here's what's going to happen. This graph is going to follow your slant asymptote as you come down through here. But then once it gets to the top, it'll start following that vertical asymptote up here. Same thing here. It's following the vertical asymptote down here. Then once it gets up to the top, it'll start following more of the slant asymptote around. So it looks something like that. So the range, it goes down forever, up forever. Your range here will be all real values. Number 8. First step is to always factor these. So the top, let's first factor out an x. You're left with x squared plus 3x minus 4. On bottom, you can go ahead and factor that. 2 sets of parentheses. You have an x and an x. Adds, multiplies will be a positive 2 and a negative 1. The top, we can go ahead and factor that. Adds to give you 3, multiplies give you 4. Will be a positive 4 and a negative 1. So let's go ahead and write that. That'll be x plus 4 and x minus 1. So therefore, that's in factored form. So our domain, we have a couple of restrictions here. X cannot be a negative 2 or a 1. Now, what happens there? You have one of each. Notice that at x minus 1, there's a factor of x minus 1 on top and bottom. So you have a hole at x equals 1, and you have a vertical asymptote at x equals negative 2 because it's not a factor of top and bottom. So if you would like to, what you can now do is you can simplify that, take out your removable, and you now have x times x plus 4 on top, and you have an x plus 2 on bottom. So you have options here to find that other slanted asymptote because, again, the degree on top is bigger than the bottom, so you will not have a horizontal, but you will have a slanted. You can divide this if you would like, or notice what we've now done. We simplified this thing down. This is now x squared plus 4x. So you can actually divide there if you would want to. Up here, you are going to have to use long division. Here, you can actually use synthetic division. So let's go ahead and find our slant asymptote here. Negative 2, we're dividing by x plus 2. We have 1x squared plus 4x plus there's no constant there. Bring it down, multiply. Add them together, multiply, and there's your remainder. So you have, that's equal to x plus 2 minus 4 over x plus 2. So therefore, your slanted asymptote will be located at y equals x plus 2. Again, just take away the remainder. Now let's go ahead and plot, well, we need to find our hole. Our hole is located at 1, but it's let's find the actual point. The way we can do that is once we remove that discontinuity, we can now plug in our 1 here. That'll be 1 times 5 divided by 3. 1 times 5 is 5. Divide that by 3, and you get 5/3. So your hole is located at 1, 5/3. So let's go ahead and put both of our asymptote lines and our hole on our graph. Okay, there's your vertical asymptote, your slant asymptote, and the hole. Let's go ahead and find our x-intercept and our y-intercept. To find an x-intercept, again, you plug in 0 for y. So you're going to take your function, set it equal to 0. which means in order for a fraction to be 0, the top must be 0. So therefore, you have two factors on top, set them each equal to 0, and you're either going to get 0 or -4. So your x-intercepts are going to be 0, 0, and -4, 0. So let's go ahead and plot those. 0, 0, there's one of them. -1, 2, 3, -4, 0 is going to be your other. We can go ahead and find a y-intercept by plugging in 0 for all your x's. Again, notice what happens. The whole top goes to 0, the bottom goes to -2. 0 divided by -2 will be 0, which makes sense. If you have an x-intercept at 0, 0, you're also going to have a y-intercept at 0, 0. And then pretty much you have your graph. Let's come down here and follow our vertical asymptote. Come up through here and go through the hole and start following your slant asymptote. Same thing on the other side. Down here, you'll follow your slant asymptote, and then as you go up, you'll start following your vertical asymptote. So there is your graph. Your range, notice that even here where you had a break, there's a y value over here that makes up for it. So therefore, your range is going to be all values from negative to positive infinity. Number 9. Step number 1, let's factor everything. Two sets of parentheses. X times x adds multiplies will be a -3 and a -7. On bottom, two sets of parentheses. X times x adds multiplies will be a -3 and a -1. So you have discontinuity at x cannot be 1 or 3. Notice you have a factor of x minus 3 on top and bottom. So you're going to have a hole at x equals 3. So the vertical asymptote must be the x equals 1. We can remove that discontinuity and rewrite our equation as x minus 7 over x minus 1. So to actually find out again where that hole is located, we can now plug it in. That hole is going to be located at 3 comma. Plug it in here and here. That's -4 over 2, which is -2. So there's the hole in your graph. Now let's find what kind of asymptote. Do I have a slant asymptote or do I have a horizontal asymptote? Again, look at the degrees. Second degree on top and bottom, or you could look over here, first degree on top and bottom. The degrees are the same. Anytime the degree on the top and the bottom is the same, you look at your leading coefficient. If you look here or the other place, the leading coefficients on top and bottom are 1, so you will have a horizontal asymptote of y equals 1 over 1 or simply y equals 1. So therefore, you will not have a slanted asymptote here. Let's go ahead and plot our vertical asymptote, our horizontal asymptote, and our hole on our graph. Okay, now that we have those plotted, let's go back. Let's find our x-intercept and our y-intercept. To find an x-intercept, you set y equal to 0. So you can take either here or here. I prefer down here. Let's set this equal to 0. The only way the only way a fraction can equal 0 is if the top is 0. So that would be an x-intercept of 7, 0. You can go ahead and plot it. 1, 2, 3, 4, 5, 6, 7 zeros right here. To find your y-intercept, we're going to plug in 0 for all of our x's. And again, it's really easy to do it here because all of this stuff goes to 0 and leaves you with 21 over 3. So you'd have a y-intercept of 0, 7. So let's plot it. That's going to be right there. So now you pretty much have your graph. Follow your vertical asymptote. And then up here, follow your horizontal asymptote. Same thing up here. You've already got where your graph's going to be, so you're going to follow it there. And then you're going to come down here and follow it here as well. Your range, the only break, you have two different breaks. And you can write this in interval notation, or you can just simply say, well, my y value will never be this because of the hole. So y does not equal -2. And it will never equal 1 because of my horizontal asymptote. Number 10. Step number 1, let's factor. Factor out the x on top, and you're left with x squared minus 1, which is difference of squares. So let's go ahead and difference of squares will factor into conjugates. So that'll be x plus 1 times x minus 1. When you factor the bottom, two sets of parentheses. X times x adds multiplies will be a -1 and a -1. Notice that you have discontinuity at x equals 1. So x will never equal 1. Now the question is, what kind of discontinuity do you have there? And this is kind of an odd situation because actually you can remove that discontinuity and think, well, I've got a hole there. However, you still have that x minus 1 left on bottom after you remove it. So that's going to force you to have a vertical asymptote. Now, could you have a vertical asymptote and a hole at the same place? Well, if you've got a vertical asymptote, that means your graph is getting closer to it. How can you have a hole and a vertical asymptote? So what we're going to do, we're going to remove that x minus 1, but you're still going to have one on bottom. So you're going to have a vertical asymptote at x equals 1. And since you have that vertical asymptote there, it's going to be hard. You're not going to be able to have a hole there as well. So let's simplify our function. We now have x times x plus 1 on top, and you have an x minus 1 on bottom. So now let's see, do I have a horizontal asymptote or do I have a slant asymptote? Since the degree of the top is higher than the degree of the bottom, I will have a slant asymptote, so there will be no horizontal asymptote. Since I have a slant, again, I can divide it here, or I would much rather divide it after I reduced it. I have on top, again, this is x squared. If I were to multiply it back out, I have x squared plus x on top. We're going to use synthetic division and divide it by x minus 1. So I have x squared plus x plus 0. You do have to include that constant term. When you divide it, bring down the 1, multiply, combine them. There's your remainder. You'll get y equals x plus 2 plus the remainder over x minus 1. So therefore, your slant asymptote, take away the remainder, will be y equals x plus 2. So let's go ahead and graph our vertical asymptote, and let's graph our slant asymptote to get ready. Okay, so there are your two asymptote lines. So now let's find our x-intercept and our y-intercept. To find an x-intercept, again, we're going to take our function and set the whole thing equal to 0. The only way a fraction can equal 0 is if the top is 0. So you're going to have an x-intercept at 0 and negative 1. So you're going to have 0, 0, and negative 1, 0 will be your two x-intercepts. So that's going to be at, here's negative 1, 0, and another one at 0, 0. And this graph does look a little bit different from what we've been doing. So now let's find our y-intercept, which hopefully you already know what it's going to be. But to find a y-intercept, you plug in 0 for all the x's. Look, all the x's on top cancel, which leaves you with 0 on top and 1 on bottom. 0 divided by 1 is 0. So you have a y-intercept at 0, 0, which you already knew because that's where our x-intercept was. So therefore, my graph will do this. It's going to follow from here. It's going to follow my oblique asymptote, my slant asymptote down through here, and then it's going to go through this point and it's going to start following my vertical asymptote. So it's going to look like this. And then we need some points elsewhere. We need to plug in something like, we can't plug in 1 because there's a vertical asymptote. Let's plug in 2 to find out what would my graph do at 2, or maybe what would my graph do at 3. And again, I always like to go back to the original maybe to plug it in, or you can plug it in here. Either way, it might be a little bit easier. When I plug in 2 and 3, here's what I get. And oddly enough, when I plug in 2 or 3, I get 6 in both scenarios. And here's why. Your graph's going to follow the vertical asymptote as it comes up. It's going to come down, go back through that point, and it's going to follow the oblique asymptote. So there's a picture of your graph. Your range now, a little bit more difficult here to find this range. And here's why. Right here, as it goes through these 2 points, I don't know what the highest, it goes a little bit higher than 0 right here. And the same thing right here, it comes a little bit lower than, what was that, 6. It comes maybe to 5.7, 5.8 right there. So what I'm going to do is I'm going to use Desmos because we've not yet got capabilities of doing this without it. So let's use Desmos to try to figure out what our highest point is here and what our lowest point. Let's find some local maxes and local mins. Okay, so here is my Desmos graph, and notice we've got the exact same looking graph, and hopefully you can see your vertical and your oblique asymptotes there. But look how easy this is now. When you click on your graph, there's that highest point there, and there's that lowest point there. So let's go ahead and plot those 2 points. Let's label them on our graphs. Okay, and there we have them. So therefore, our range, we're going to go from negative infinity up to this y value, which was 0.2. And then we jump from there up to this y value, which was 5.6, and we'll continue there on to positive infinity. Now 0.2 and 5.6 were both included in your graph, so therefore they were point on your graph, so make sure we include them on that. Number 11. Let's go ahead and factor the bottom here. The top is just a 16. Let's pull out a 4x, and we're left with an x minus 2. Now that will clean up a little bit. We can cross cancel our 16 and 4, and that leaves you with a 4 on top and an x minus 2 on bottom. So therefore our discontinuity, our domain x cannot be 0 or 2. So let's find out what happens at 0 or 2. Notice that there's no x on top and there's no x minus 2 on top, so therefore there are no holes on this graph. So therefore both of those would be vertical asymptotes. So at x equals 0 and at x equals 2, we have vertical asymptotes. Now let's figure out, do I have a horizontal asymptote or do I have a slanted asymptote? Since the degree of the top is 0, that's x to the 0, the degree of the bottom is 2, so therefore anytime the degree on top is smaller than the degree on the bottom, you'll have a horizontal asymptote at 0. And you will not have a slanted asymptote in this case because, again, this is not improper. The degree on top is not higher, so there's not a slanted. So let's go ahead and graph those vertical and horizontal asymptotes. Okay, now let's find our x-intercepts and y-intercepts. To find an x-intercept, set y equal to 0. So there is absolutely no way this top can equal 0, so you will not have an x-intercept. And again, the reason for that is because the horizontal asymptote at your x-intercept. The y-intercept, we're going to plug in 0 for all the x's, and notice what happens. The bottom goes to 0. You have 16 over 0, so you will not have a y-intercept either because of, again, the vertical asymptote there. So we don't have any points on this graph, so we definitely need to plug in some points to figure out what's going to happen in each of these domains, what happens in each interval. I'm going to make me a t-table, and I'm going to simply plug it in. This is the cleanest probably, so we'll plug it in right here. Just pick some points in each interval, plug it in. Let's see, we'll do a maybe -2 and -1. Can't plug in 0, but we can plug in a +1. Can't plug in 2, but you can plug in 3 and 4. Plug in these x values in. Let's see what we get. Okay, so there's the x values I plugged in. That's what I got. And this is kind of cool because look at how symmetrical this thing is. This is definitely going to be an even function because it does have, well, no, it's not, because it's actually shifted over 1. It's nearly an even function, but it doesn't have y-axis symmetry because here's your y-axis. It nearly has that symmetry, but it does not. So therefore, let's follow our horizontal asymptote. Let's go through our points and then follow our vertical asymptote. So there's that portion of the graph. On the other side, it's going to do the exact same thing. So let's come up and follow our vertical. And again, down here, let's follow our horizontal. Then in the middle, notice where your point is. It's going to come down, follow the 2 verticals on each side. So there's a picture of your graph. So now we can do the range. The range goes from -infinity up to this point right here, which was, let's see, -4, I believe, on the y-axis. Then it jumps up to your horizontal asymptote, which is at 0, and it goes from 0 to positive infinity. But since 0 is a horizontal asymptote, there's not a point on your graph at 0, but it does start there. Okay, last one. Step number 1, let's factor everything. Top, you're going to factor out an x. You're left with x squared plus 4x minus 12. The bottom is difference of squares, which will factor into conjugates. So you have an x plus and an x minus 2. Let's go ahead and factor again that x squared plus 4x minus 12. Adds to give you 4, multiplies to give you 12, will be a +6 and a -2. So let's just erase that and put x plus 6 and x minus 2. So you have discontinuity at x equals, so x cannot equal, let me try that again. -2 or +2. The bottom cannot equal 0. So therefore, what kind of discontinuity is that? I have a hole at x equals 2 because I have removable discontinuity there. I have infinite discontinuity at x equals -2. So you have a vertical asymptote at x equals -2 because, again, x plus 2 is not a factor of both. So let's go ahead and clean this up. So now you have x times x plus 6 over x plus 2 after you remove that discontinuity. So now we can find out exactly where our hole is located. When you plug in 2 into this new function, it gives you 2 times 8, which is 16 over 4, which is 4. So you have a vertical asymptote and a hole there now. Now let's check out our horizontal asymptote versus slant asymptote. Since the degree of the top is bigger than the bottom, this is an improper fraction. Let's divide. You can divide your original or you can divide your new here. Just to give us extra practice, let's use some long division here, and let's divide our original. Okay, so we have the top divided by the bottom. X squared into x to the third goes x times. Distribute that out. That'd be x to the third plus, notice I put my 0x in there because I was missing that term. Let's subtract. X to the thirds cancel, leaves me with 4x squared minus 0x squared, which is 4x squared. -12 minus -4 will be -12 plus 4, which would be -8x. Bring down your 0. X squared into 4x squared goes 4 times. Distribute gives you 4x squared plus 0x minus 16. Subtract. Cancels. 8 minus 0 is going to be, or -8 minus 0 will be -8x. 0 minus -16 will be plus 16. So you have minus. Now you got to be careful here because if you put a minus here, you can't put 8x plus 16 on top because it's only minus the 8x. So you could do a plus this stuff over x squared minus 4, or if you wanted to put a minus here, you would have to change this 16 to a -16 to get it to work out right. So therefore, dump the remainder, and your slant asymptote will be located at y equals x plus 4, and you will have no horizontal asymptote. So let's go ahead and put those on our graph. Okay, so there's my asymptote lines and my hole on my graph. So now let's find our x-intercept and our y-intercept. Find an x-intercept, set the whole function equal to 0. The only way a fraction can equal 0 is if the top is 0. So set the two factors on top equal to 0, gives you 0 and -6. So my x-intercepts are at 0 and -6. So that's going to be here and 1, 2, 3, 4, 5, 6. -6, 0 right there. Your y-intercept, set all the x's equal to 0, gives you 0 over -4, which is also 0. And again, you can see if you have 0, 0, and 1, you'll have 0, 0 on the both. Let's connect our dots and follow our asymptote lines, and our graph will look something like this on this side. And same thing is going to happen on the other side. Follow your vertical asymptote up, follow your slant asymptote down, and there's the other side of your graph. So your range, notice that there is a break in the graph, but there's a y value over here that compensates for it. So you'll have an infinite range here, in -infinity to +infinity.